Hello there. Let's continue with this interesting topic, chemical equilibrium. Not before checking one of these 10 lessons from Einstein. We can learn from the great minds. This one says, follow your curiosity. He said, I have no special talent. I am only passionately curious. So that invited us to wake up our curiosity side of our mind. Le Chatelier's principle, chapter 14, chemical equilibrium. Le Chatelier was a chemist, French chemist. He made some important developments in the chemistry area. And one of them is something that we call in chemistry Le Chatelier's principle. When you hear about Le Chatelier's principle, you're talking about chemical equilibrium. That principle helps us to understand how equilibrium works and also to make educated predictions regarding how the equilibrium moves, how the equilibrium shifts in a chemical reaction when you disturb the equilibrium. So he said this on this translation, you can read it in many ways. Different textbooks chose a different translation, but more or less what he said was that, or he found, not just he said, he found experimentally that if a change is made to the conditions of chemical equilibrium, the position of the equilibrium will readjust so as to minimize the change made. In other words, if we disturb the equilibrium, chemical equilibrium, if we break that chemical equilibrium, the system will readjust to counterattack or to minimize the change you are making to the equilibrium. I mentioned it before, it's a nature process, it's a spontaneous process, you don't have to do anything. The system will shift to a new position of equilibrium. And there are basically three ways to disturb the equilibrium. So far, we can discuss three ways that we normally use to disturb the equilibrium. And you can ask, why do you want to break the equilibrium? Sometimes we want to shift the reaction to the right or to the left. I mentioned in a couple examples in the previous recording that sometimes the equilibrium is not good for your intentions when you're working with chemical reaction. Sometimes you want to make more products, and the equilibrium for that reaction doesn't allow that, because once the equilibrium is established, you know the concentrations of all reactives and products will remain constant. So you may want to push the reaction in either direction, to the right or to the left. And we can do that. We can trick the equilibrium by disturbing the equilibrium. However, we know the system will reach a new equilibrium by itself. So here are three different ways, basically, to disturb the equilibrium. We can disturb the equilibrium changing concentration. We can disturb the equilibrium by changing temperature, or we can adjust pressure volume conditions to disturb the chemical equilibrium. So let's see the first one, changing concentration. Let's use our signature chemical reaction that we always use as an example. And that one is the formation of ammonia from hydrogen and nitrogen. So we have N2 gas plus H2 gas to form ammonia and H3 gas. So we know the balancing stoichiometric coefficients are 3 for hydrogen and 2 for ammonia, and now our reaction is balanced. Remember, I always suggest check with if your chemical equation is balanced. So let's start making some changes. Let's start playing with this equation to apply the Ch14 principle. Again, the Ch14 principle just help to make predictions when you disturb the equilibrium, knowing that the system will work by itself spontaneously to gain the equilibrium back, regardless of what you did, what changes you made. And you can make these three types of changes. Changing concentration, changes you can make to disturb the equilibrium. Again, I'm going to write them here. Changes we can make. To the reaction conditions. To disturb the equilibrium. And those changes, those changes Can be voluntarily or involuntarily. You can willingly make those changes, or you can, or sometimes we just make a mistake and we make a change in the reaction conditions, but the system, the reaction will readjust to minimize the change that you're making. So there's 3 ways to make changes. One, I mentioned it, is concentration. You can change concentration of reactives, of any reactives of products. The art at the equilibrium. This is your system, this is your reaction, you have reactives making products. At the same time, products are making reactives, and the speed of the forward reaction equals the speed of the reverse reaction. That's chemical equilibrium. And you can make changes. So basically, in general, this is what happened. If you add, if you add, let's put it that with the black color. I like that black color here. If we add reactives, we add chemicals, we add concentration. When we add moles, so we're changing the concentration. It's moles per liter, and the volume of the container is fixed. The volume of the reaction chamber is fixed. It doesn't move. So when we add moles here, moles of reactives, and number of moles of reactives, you are changing the concentration of reactives, any reactive. So when we add, according with the Ch14 principles, when we add reactives, you force the reaction to shift to the right, shift to the opposite side. Why? To remove, this is the way the system readjusts, to remove the excess you are adding, the extra moles you are adding. So it will react these extra moles, extra molecules of reactant, they will react each other in your reaction to make more products. As a result, you're forcing the reaction to make more products. You see, if you add here, the reaction shifts to the right and product goes up. Make sense? That's according with Le Chatillon's principle. What about if you add reactives here on this side? So let's add reactives on that side. Now I think you got it, and now I think you can make interesting predictions here. Let's say we add products here. Guess what's going to happen? You are adding extra moles of the product, any of the products, or all of them, and they will start reacting together to use whatever you are adding extra. Because you have the system green is already at equilibrium, is at equilibrium. So you add something extra that disturbs the equilibrium concentration of reactives and products. So the system will use that extra. How? Reacting together. It's going to consume the extra material you're adding, and that by consuming this makes sense that if you consume something, it's going to produce something, right? So it's going to shift your reaction to the left. So here we say shift to the left. And here it says shift. And this first process going that way, shift to the right. R. And as a consequence of that, adding here the reaction shifting to the left, then what happened with the concentration of the reactives? As a result of that, addition here will increase. Concentration of reactives will go up. That is when you add either reactives or products. What will happen if you do the opposite? You don't add, but you take out reactives or products. That's changing concentration, right? Because you take moles out, so you change the concentration. So let's take, for instance, here, let's use some red. You take out some reactives. Somehow you have a pump and you can suck out reactives. Especially the air gases, it's easy to do it. So you take out reactives, you pump out reactives, and what's going to happen? What do you think is going to happen? You're taking out, you're disturbing, this system is already at equilibrium, the green one is already at equilibrium, and you take out reactives that disturbs the equilibrium. So what is the response of the system? What is the response of the reaction naturally and spontaneously? It will try to replace by itself whatever you're taking out. How? Well, you say, okay, products make more of this. So that shifts the reaction to the left. To the left. You take out reactives, shift the reaction to the left to make more reactives to replace whatever you're taking out. And by doing that, what happened with the concentration of products? They are being consumed very quickly to make more reactives. So concentration of products will go down. Yes, will go down. Hold on. I put the arrow in the wrong direction. Yeah. So the concentration of products goes down. I have to put it here so you don't get we don't get misunderstanding here. Concentration of this goes down. Here means it's taking out, and over here how concentration is changing. Concentration goes down. I should put it here, concentrations. Concentration goes down. All right? Probably it's better if I use, you see, I'm just discovering a better ways to represent this chemical concept. I just realized that if I use the concentration symbol, concentration goes down for the red one. For the brown one, concentration goes down. And for the black one process, concentration goes up. Now I can place that anywhere. Here is the direction you're adding taking out, and this, oh, sorry. This is adding, and this is taking out. And this is concentration. Concentration goes up. Oh, this is really interesting. This is something really interesting here, because I just realized I can improve my teaching. At least the way we are writing this. This concentration goes up. And I just realized that I did something. Yes, probably you realize that too. That here, for the brown one, we are adding products. We're adding products, shift the reaction to the left, concentration of reactives increases. And of course, concentration of products decreases. Here we are adding reactives, reaction shift to the left, to the right, concentration of products increases. This one, we are taking out reactives, reaction shift to the left, concentration of products decrease. And the next situation will be since I'm using better symbols, I can now put it on the bottom as I had it before. What happened with these concentrations here? We take this out, so concentration of products goes down. Because they are being used to make more reactives to replace whatever you're taking out. Now, the next possible situation is when you take out products. Take out products. What will happen? When you take out products, concentration of products goes down. Shifting the reaction to the right to replace whatever you're taking out. Therefore, as a consequence, reducing the concentration of reactives. So concentration of reactives goes down. This little table we just created here, you and me, is very useful. You can write it out in a cheat sheet, so you will always remember that process. And that applies for any situation, any equilibrium situation. That's it. Everything is summarized here when you make changes on the concentrations. The second change you can make is changing temperature too. Changing temperature of the system. So changing temperature of the system will have effect also in the direction of the position of the equilibrium, direction and position of the equilibrium. And that will depend on whether the reaction is exothermic or endothermic. So let's analyze everyone. So it depends. If the reaction is exothermic, when reaction is exothermic. So let's use one reaction. Let's use one reaction that is exothermic. Let me check. I think I had that information somewhere. Whether or not. Oops, this is goes down. This goes down. Let me see it here. Okay, let's figure. There you go. You see this one here? This is a trusty. Let me see. Yeah, I remember this number now. That's what it is. So this looks a good number. I've seen it before. And now, not that one, but this one. Okay. So I just found that a reaction there. Let me see if I can do this trick here. There you go. This is very interesting. So we have this one. This is the one I was looking for. Let's increase here the size. Let's make it bigger so you can see it better. Oops. Yeah. Here. Let's do 20. Okay. All right. And this is capital J. Kilojoules. All right. So here is our this is our star reaction, our signature reaction, and it's called a thermochemical reaction. It's called thermochemical because it's showing the enthalpy of the reaction. This is the standard enthalpy of the reaction. And that's what I was looking for. When we want to analyze effect of temperature in the equilibrium, we must know delta H of the reaction. If you want to apply Le Chatelier's principle, and you want to change temperature of the system, and you want to know in what direction the equilibrium will shift when you make that temperature change, we must know the value of delta H. More importantly, not only the value, but the sign. Oops, here we go. There you go. Much better. So you can make things better. That's how we should write it. Equation, and after the equation, just the delta H. And here, it's not the value what we want to know, the magnitude, but the sign. The sign. That is what we're looking for. In this case, it's negative sign. Now let's remember what is the meaning of that. From the Chem 11. When you see delta H negative means what? Has only one meaning. And I know you remember. I know you remember. Yes, you can say the reaction is exothermic. You say the reaction, oops, that's very important. The reaction, this reaction is exothermic. Why? Because you know the sign is negative. Because delta H of that reaction, this is delta H standard for the reaction, is negative. Is negative. You can say it this way. You can say, I'm using different ways to represent what we're saying in chemistry. You say it's less, it's less, it's less than what? Than 0. In other words, is negative. You see, two different ways to say it's negative. You say delta H of the reaction is less than 0, that means it's negative. Or you can say the delta H of the reaction is negative. So I mentioned it, two different ways to say it, because those are the two different ways you can read it in a textbook, so that you will understand. A lot of people get confused when they're reading. I say, I don't understand anything chemistry, because you don't know how to read chemistry. And if you learn only one way, and the textbook you're reading is using a different way, that's it. For you, you won't understand it. Some textbooks says that the delta H is negative. Other textbooks will show you this. Look, and looks complicated. When you see this in a textbook, that looks scary. What is that? You see? Now you're learning. Now you learn what is that. And you can read actually chemistry.
Okay, I found this on the web for how do you write career movie stuff. Check it out.
That was city. City. Okay. So this reaction is exothermic, but that is not enough. When you say that, it's not enough because that can have different meanings or applications. There's only one meaning, I know. The exothermic means the reaction is what? Releasing energy, releasing heat. But what I'm saying is not enough for you. You need to add more information about that, what's going on in the process. You said the reaction is exothermic, and just like that, is open to get misinformation. You say the reaction is exothermic. In what direction? You need to show the direction. You need to tell the direction. In what direction the reaction is exothermic? In the way the equation is written. You see, now I showed you how to say that at the beginning, and that's one of the reasons. We need to show in what direction the reaction, in this case, is exothermic. So the equation there, this equation, is written the way. It's written from left to right. And also we know this is a equilibrium. This is a equilibrium reaction, so we should have the double arrow there. So the way it is written, the reaction is exothermic. Now it's clear. There's no way for misinterpretation. The reaction is exothermic this way, the way it is written, from left to right. So let's put that here. Let's write that here. From left or to the right, that reaction is exothermic. To the right. We're talking about the direction of this reaction. This reaction, the way it is written, is exothermic. So what happened with the opposite direction, with the reverse reaction? This is to the right, and this is to the left. What happened with the reverse reaction? We call this the forward reaction, and we call this the reverse reaction. If the reaction is exothermic for the forward reaction to the right, therefore the reaction is endothermic. Endothermic means absorbs heat. Exothermic means releases heat, makes heat in that direction. In the opposite direction, absorbs heat, is endothermic. How do you write this in a crazy way? You say delta H, standard of the reaction is what? Plus 0. That means for the reverse reaction, delta H you say delta H delta H of the reaction is what? Plus 92.2 kilojoules. For the previous one, you will say the reaction is delta H of the reaction is negative 92.2 kilojoules. For the reverse reaction, the delta H of the reaction is plus 92.2. So just change the sign. Right? To the right is negative, to the left, therefore, has to be positive. It's actually the same magnitude, same number. And we don't care about the number at this moment. We just care about the sign of that delta H. The sign tells you whether you have exothermic or endothermic reaction. Negative for endothermic, that means heat is coming out of the system. That's the sign notation to represent if work or heat is done on the system or the system is doing work or releasing heat to surroundings. We'll explain that in the future chapter. So for this case here, you always need to say in what direction. All right. So let's apply the Le Chatelier's principle, changing temperature of the system on this reaction as it is written. On Le Chatelier, help us to understand the process. Okay, now let's make the little changes here. This time I have to write the equation again. We'll have more room here. So you have N2 gas plus 3H2 gas in equilibrium with 2NH3 gas, and delta H for the reaction is negative 92.2 kilojoules. What happened with the equilibrium when we increase temperature of the system? What will happen? Right now, this system is at equilibrium. Right now, it is at equilibrium. Let's increase temperature of the system. Le Chatelier's principle says that when you increase temperature on the system will shift in the direction that absorbs the heat you're adding. And that makes sense. You got something hot, and you increases the heat, well, the system will try to refresh a little bit to cool down, right? Too hot. So automatically, spontaneously, the reaction or the system responds to that change by going towards the direction that absorbs the extra heat you are adding. That makes sense, a lot of sense. You are outside in these sunny days, what is the tendency? To refresh. Well, you drink a lot of water to cool down your body. You fan your body. You add water. You jump into the water. You get inside where the AC is on. So, similar thing happens with the reaction, which is the equilibrium, and you add heat. This reaction, as it is written, is producing heat. Look, the sign is telling you that. This reaction is producing heat. How much heat? Some 92.2 kilojoules per mole, per every mole. So if we increase heat here, let's say, let's add heat. Let's heat this up. Temperature up for the whole system, right? You increase temperature of the whole system because you have that on a vessel in a container. So in a container, you have everything, all the mixture there, nitrogen, hydrogen, ammonia, everything there. So you heat this up using flame, using any heating device. You are not just heating nitrogen or this or that, no, you are heating the whole system. And the system is already producing heat. The system is producing heat. Q, right? Energy is producing heat. The Ch14 principle says if you add heat to something that is producing heat, the reaction will shift in the direction that absorbs that extra heat. So if this direction to the right is producing heat, then the reverse reaction is absorbing heat. So now you tell me in what direction will this shift when you add heat? The reaction, the whole reaction will shift to the left. Why? Because the reaction to the left, the reverse reaction is endothermic. The opposite situation, what happened when we decrease? Let's cool this down. That's the good thing about using colors. You can represent different things using colors. So let's cool down. Usually blue represents cooling, right? And red, hot. So temperature down, we're cooling the system, the whole system, everything. In what direction the reaction shift? Makes sense, right? To the right. To the direction that releases heat. To minimize the change you are making here. You're cooling down, you're taking out energy. So the reaction is to run to the right to make extra energy you're taking, to make up for that energy you're taking, to heat it up a little bit. Because normally it likes, the way it is written, normally likes to produce energy. Going from high potential energy to lower potential energy. And that's why what most of the systems loves to do is spontaneously, to decrease internal potential energy of the system to become a lot of times more stable thermodynamically. All right. So this is the analysis we do when we make changes on temperature. The next change is when we change the pressure of the system or change the volume. Changing the pressure of the system, and when we change the pressure of the system, we can also change the volume. There are two ways to change the pressure. By changing volume, we'll change the pressure too. Or you can change the volume by changing the pressure. This is true when you work with gases, because gases are compressible. And if we have a system here like this, and we have this little machine here, this simple device. And do you know the name of this device? Do you recognize this one, this device, the whole thing? What is the name of this? This is called a piston. It's very useful to understand the behavior of gases. A piston is a system, it's a system here, it's a closed system. You put gas here. And the interesting behavior of this simple device is that you can change the volume. And this is actually the piston. This is called the cylinder. This container is the cylinder. And this is actually the piston that wants to go inside. Inside goes up and down like a syringe. Syringe is a form of piston. Well, but the syringe has an opening here. This one, the piston, is closed. So once you put n number of moles of material here, gases, that stays there, it's constant. And you can change the volume. You can press down. And how do you press this down? At pressure. So add pressure, pressure up, volume down, volume down. Pressure down, you take out the piston out, you pull out the piston. What happens with the volume? Volume goes up. Right? You take this out, you pull this out, the piston, and the volume will increase. So volume will increase. Wow. We just discovered what Boyle's discovered a few centuries back. You remember that? Boyle's law? PV equals K. Or, in other words, the volume is inversely proportional to the pressure. All right, that's gas law, ideal gas laws, Boyle's law. That's from your chemistry level. Boyle's law. All right, so let's apply that. So remember, this is to remember that we can change the pressure by changing the volume, and you can change the volume by changing the pressure. And some problems will tell you, for example, the volume of the container was reduced. And then if you don't remember this part, you will be crazy because you say, so what? Well, so what is that? If you decrease the volume of the container, that means the pressure is increasing. The pressure of the system is increasing. If you increase the volume of the container, then the pressure is decreasing. They are inversely proportional. So this is a very important piece of information. Keep that on mind, especially when you're solving problems. That's one part. The second part of understanding this is regarding the chemical equation. I need to write the equation again. N2 gas plus 3H2 gas in equilibrium with 2NH3 gas. So let's read this equation. You can say, when you're reading this equation, you can say 1 mole of N2 reacts with 3 moles of H2 to form 2 moles of NH3. That's one way to read it. And since we have gases here, we have gases. Another way, maybe you never hear about this way to read this homogeneous reaction, is 1 volume of this gas reacts with 3 volumes of this gas to form 2 volumes of that gas, ammonia gas. And you can read it this way when you have gases on. Why? That's thanks to another guy, Avogadro's law. Avogadro's. He found that molar volume of any ideal gas. Molar volume of any ideal gas is 22.4 liters per mole. 1 mole of any gas at STP conditions. Remember, for gases, STP conditions, standard temperature and pressure, temperature is 0 degrees Celsius, and pressure is 1 atmosphere. That's for ideal gases. For thermodynamic standard conditions, temperature is room temperature. Now I'm talking about ideal gas. So the ideal gas standard temperature is 0 degrees Celsius. So we can read it this way. So that means 1 mole of any ideal gas at this condition occupies always the same volume, 22.4 liters. And we can say here safely 1 volume of this gas reacts with 3 volumes of this gas to form 2 volumes of that gas. And that's the concept we are going to apply here to understand this better. So according with Le Chatelier's principle, he says that when we increase the pressure of the system, the system will shift to the side that makes less volume. That's the way the system responds to the change by decreasing the volume. Why? Because when you decrease the volume, here, look at the system here, this system. When you decrease the volume, you are decreasing the pressure. Why? Because remember, in this system, reaction chamber, the walls are fixed. It's not a piston. It's a closed system with the fixed walls. So this cannot behave like a piston, the changing volume here. Here you increase the pressure, inside it will expand. The volume will expand. There's an expansion there. And the volume you increase the pressure, the volume goes down, so it compresses. It compresses there. So you increase the pressure, the volume goes down, it compresses, so producing a lot of stress on these molecules. They feel compression, they are closer each other. You are increasing the pressure. And how do you relieve the pressure in this system? Increasing the pressure, and the way to release the pressure there, since this cannot move, is make less volume. How? Well, making less molecules. So that's why it's important to count the volumes. So it says it goes to the side that makes less volume. In this equation, as it is written, what side is making less volume? Well, let's count here. This reactive side, how many volumes? 1 volume plus 3 volumes. That makes 4 volumes on that side. On the product side, the reaction is making 2 volumes. So you have 3 molecules here, and 1 molecule, that's 4 molecules occupying a space. When they react together, they make only 2 molecules that occupies less space. But if we count moles, now we have a lot of space. Remember, 1 mole occupies 22.4 liters at STP. So that's a lot. So imagine here we have 4 volumes. That's a lot of space. It's taking up, makes a lot of pressure inside the container, because the container has fixed walls, so they have nowhere to go. You cannot expand this volume to release the pressure. Rather, they will react together to reduce the number of molecules inside the container. In other words, to make less volume. And the reaction will shift to the right. The reaction shifts to the side that makes less volume when you increase pressure. And the opposite happens too. What would happen if we decrease the pressure of the system? If you decrease the pressure of the system, then the reaction shifts to the opposite side. Now they have more freedom, there's more freedom to get back to decompose ammonia into N2 and H2 gases. So that's how we work with pressure changes in the equilibrium systems, equilibrium of gases. We apply these concepts, we can solve any problem. I gave you all the tests here. I gave you all the tricks here. So changing the volume, I already explained that. Changing the pressure, I already explained that. Now this one, catalyst. That's important. These two situations are very important too. We need to remember this. What is a catalyst? Catalyst is a chemical substance that changes the speed of the reaction. It could be to speeding up the reaction or to slowing down the reaction. So change the kinetics of the reaction. But catalyst will not participate in the reaction, the actual reaction. So it's not part of the products, it's not part of the reactives. It helps the reactives and affects the kinetics of the reaction to change the speed. When we add catalyst to a system that is at equilibrium, the catalyst will not affect the position of the equilibrium. Why not? Because remember, the equilibrium, at the equilibrium, the speed of the forward reaction equals the speed of the reverse reaction. And if catalyst is affecting the speed of the reaction, so the speed of the forward reaction will be the same as the speed of the reverse reaction. So there's no effect in the position of the equilibrium. You can add catalyst and the position of the equilibrium will not change. In other words, when you add catalyst to a system that is at the equilibrium constant will not change. Remember, the way, the most effective way to change the equilibrium constant is changing the temperature only. Now, adding an inert gas at constant volume It's important to say this a constant volume because we are not changing the pressure. So only one condition is being changed, adding inert gas. What is an inert gas? Inert gas is a gas that is not participating in your reaction. It's inert, it's dead to your reaction. Usually we use noble gases. Noble gases are inert, especially helium, argon, neon. They are inert. They are not interested on reacting, so they will not affect your reaction. Therefore, will not affect the position of the equilibrium of your reaction. Why do you want to add inert gas to your system? Because you want to displace air, for example. You don't want air on your system. You don't want oxygen in your system. In other reactions, for example, nitrogen will be inert. Your reaction doesn't react. Any of your reactants doesn't react with nitrogen, so nitrogen gas will be inert. So sometimes you can use nitrogen, depending on what type of reaction you have. So no changes in the position of the equilibrium. Now, calculations. Let's do a couple problems here. Let's do a couple problems to apply all these concepts. Let's do this, for example. So we have this reaction. N2O4 gas decomposing into 2NO2. And I'll show you step by step the analysis and do critical thinking on this reaction. So you can apply the same procedure, same concepts to solve any other problem. So we have N2O4 gas to form 2NO2 gas. We read the problem carefully and we write down, I like to write down all the information given in the problem. It says if 0.0350 moles of N2O4, so let's write that down, 0. I'm going to write it here on top, 0.0350 moles. Careful, read the units. It's placed in a liter flask. Oh, so it's moles per liter. So now we have concentration. So this is going to be concentration of N2O4. This is concentration of N2O4. So you have to be careful because depends on how many liters of the container, then you can calculate the concentration. So always read that. Let's say if the reaction say is placed in a 10 liters, so you have to divide by 10 liters to find the concentration. So don't just put that number over here right away. Yeah, check, make sure you have molar concentrations, moles per liter. So that was initial. This is initial amount of N2O4 in the system. Now we can write right here. Usually when you are working with equilibrium, do the ice table. It's the safe way to organize your data. And then you can do the analysis, 0.0350. We don't have to write the units because we know ice table uses only molar concentrations. And what is the initial amount of this? 0. Nothing. We didn't put anything there. At 25 degrees Celsius, very important. Temperature is 25 degrees Celsius. Oops. Okay. No panic. 25 degrees Celsius. Okay. It says at the equilibrium, they measured it at the equilibrium 0.0292 moles per liter of N2O4 and 0.0116 moles per liter of NO2. I guess they're asking for the equilibrium, find the equilibrium constant. You see? They're asking, what is the equilibrium constant? K sub C. So the equilibrium constant, K sub C, equals, and we always write the expression. It's better to write it down. So concentration of NO2 square, yeah, over concentration of N2 which is N2 O4. And we don't know. That is our unknown. We need to find that out. That's going to be very easy because we already know equilibrium concentration. Remember, this is the expression of the equilibrium law. So we plug in only equilibrium concentrations, this one. These values here in the ice table is to find equilibrium constant. These values here at initial data helps to find Q sub C. Since we already know the equilibrium concentration, we don't need to do the change. But let's do the change here just for the sake of practicing. If you were to do the change, what would you say? This reaction is going to the right, so it's going to use up a little bit of this, or some of this. So it's going to be minus X, and it's going to make that 2 times X. You can actually know by how much is that, because you already had these 2 numbers, just find X. So 2.0350 minus 0.0350 minus X equals the equilibrium. It's given already, so you can find X by how much that was changing. And here is going to make 2X. So this is your 2X. And here 2X equals 0.0116. You already know that. So half of that is X. And that's what you have here. This is just to practice a little bit of doing a little bit of critical thinking, because a lot of times you have to use this information, just reviewing. It's important to review, to apply this, to do critical thinking. In this particular problem, we don't need that information. That's what I initially left it blank. Because the question is, what is the equilibrium constant? And equilibrium concentrations were given. Just plug in your mass action law, mass action expression. All right. I mentioned it before that sometimes when you are solving equilibrium problems here at the and you are dealing with these equations, sometimes you arrive with the quadratic equation I showed you last time. So you have to do this. In the practice, please practice how to solve the quadratic equation. I ask your little sister, your little brother to ask them for assistance so they can help you to solve this problem if you forgot. And they find some problems and solve it, because you may have one, probably in the test, I'm going to place only one equation where you have to use the quadratic equation, only one. And I'll give you 5 minutes to do that. 5 minutes to solve a simple quadratic equation is fair if you have practice. If you have no practice solving this math equation, then you can spend probably 1 hour or 2 hours or 3 hours or 24 hours to solve one simple problem. You need to practice, definitely. We can use either K sub C or K sub P. Let's do this one. This is a classical problem. Let me write it. I like to rewrite my equations so I can work with that. I have a lot of room to work. N2 gas plus O2 gas in equilibrium with 2NO gas. Let's see what information is given, and let's put it here. Says nitrogen and oxygen react to form nitrogen monoxide. So it says with Kc equals, oh, Kc is given. I didn't leave room here. Usually we write Kc here. I'm going to put it here. Kc is 4.8 times 10 to the negative 31. And the temperature temperature is 25 degrees Celsius. And the pressure is 1 atmosphere. Okay. So those are extra information is given. That means the conditions of the experiment. This is the valuable information here, the Kc. So it's given. Now the problem. It says in air at 25 degrees and 1 atmosphere, the nitrogen concentration and O2 concentrations are initially, so that's initial concentrations. Let's put it here, it's given already in concentration because it's molar. So you can plug that number directly here. Be careful when they are giving you amounts in moles or grams. So that means you have to calculate the concentration. You need to find in the problem what is the volume of the container so you can find the molar concentration. If you have moles, just divide moles by the volume of the container to get molarity. If you have grams of the gas, what about it? Let me extend this problem a little bit. Remember, I'm doing all critical analysis possible for you, so I have to cover all corners for you. So you do the analysis very quickly on your particular problem. That's how we do solve problems. We have to do critical analysis of the problem initially, analyze what information is given, what information is not given, what you can do, what information you can find or rearrange or recalculate in order to solve the problem. Let me give you these situations you can face solving this type of problems. Let's say the problem, I'm going to throw numbers here. Let's say the problem says the N2 concentrations of O2 are initially, let's say, for N2, 35 grams. Of N2. I'm just going to modify this one. Initially, in the container were placed 32.00 grams of N2. And everything else the same. What are the equilibrium concentrations? So what I'm saying is, read carefully, read the units to see what you have. Again, if here they give you moles, so you need to find concentration. Find what is the volume of the container. And let's say somewhere the problem should tell you in that case, the volume of the container is 10 liters. So that changes everything. If 1 mole is given here, so therefore the concentration is 0.1. 1 mole divided by 10 is 0.1 mole per liter. And that's the number you put here, molar concentrations only. You don't put here moles, you don't put here grams in it. What about if the problem gives you grams like this? How do you find the volume? I mean, how do you find the volume is given? Volume of that container. Volume of the reaction chamber, where you're putting all these chemicals inside. How do you find the molarity? Well, we know if we have grams, then the next step is to find moles. And moles equals grams over molar mass. Once you have moles, find molarity. That's the sequence. That's the process you need to follow. So from here, moles of N2 will be the grams given, which is 35.00 grams over molar mass. What is the molar mass of nitrogen gas? Atomic mass of nitrogen is 14 times 2 is 28. So it's 28 grams per mole. 28. That will be the molar mass of N2. 28 grams per mole. So what is the concentration? So it's going to be 35 You go here, 35 divided by 28. Let me do it here. I'm assuming you are doing it on your own calculator too. Just 35 divided by 28, and that is 125 moles. 125 moles. .25 moles. Grams divided by grams per mole. Oh, this is mole. Gives you moles because grams cancels out. And now from here you find molarity, and you know molarity equals moles over volume in liters. So molarity here equals moles. We just found 125 mole divided by the volume in liters, which is 10 liters from here. Yeah, it's given supposedly. Yeah. So molarity equals 0.25, 125, 0.125 moles per liter. Now you can place that number over here in the ice table, not before. So be careful when that, read carefully the information, and sometimes you have to do extra job in order to use it. Let's go back to solution of this problem. So initial amounts are given already in molarity, so I can put that here. For N2 is 0.033, and for O2 is respectively here 0.00810. Any initial amount of NO? No. So the initial amount is 0. And notice that we don't have equilibrium concentration. It's not given. Why not? Because they are asking for that's actually the question. What are the equilibrium concentrations? And the equilibrium constant is given, so we need to write the change here. The change. So the change, very quickly, you already know how to do it. I explained many times the way to do it. Since we have reactives, these reactives works together to form products. So this is going to be used, this is going to be formed. So it's going to be used, that means minus by minus X factor minus X amount out of the initial, here minus X, and this is going to make 2 times that amount, 2X. And then we have the equilibrium. We have the equilibrium condition. At the equilibrium, we'll have 0.033 minus X here. And over here, 0.008110 minus X. Let's write that between parentheses. And here, on the other side, I like to make a border here so we know what is reactives or what are the products, and we don't mess up the numbers. It's going to be 2X. That will be the equilibrium concentration. And we need to find the equilibrium concentration of this. That means in order to know the equilibrium concentration of this, we need to know X. X is not the equilibrium concentration. X represents the change during the process towards the equilibrium. This is the equilibrium concentrations. 0.03, the initial minus the change will give you the actual equilibrium concentration of N2. And this term here will give you the actual equilibrium concentration of O2, and 2x will be the equilibrium concentration of NO. So how to find x? Very simple. Let's use the mass action expression. So we need to write the equilibrium law, Kc equals concentration of NO squared over concentration of N2 times concentration of O2. Remember, always verify your equation is balanced. This equation is already balanced, so always verify that before you attempt to do this. And for our good fortune, we know this value is given. 4.8 times 10 to the negative 31. Let's do a little bit analysis. Look look this value. Is small or big? This is a very, 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 very small number. That means that the equilibrium constant is a very, very small number. What does it tell you about this reaction at the equilibrium? It tells you that this at the equilibrium, how do you get a very small number when you have a fraction? That means this number has to be very small and this number big, right? That's how you get a small number on a fraction. Small number, big number, that makes small numbers. So that means at the equilibrium you have, in this case, very, 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 very small number here and huge number here in order to produce this little number here. 4.8 times 10 to the negative 1. That is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000ɔ Means what? That at the equilibrium, the reaction is basically, we can say, it's not making products. It's making very, 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 very little amount of NO. That is the behavior of that reaction. All right. And we have to deal with this. Now let's plug these expressions of equilibrium concentration into this mass action expression. Let's plug in. So we'll find what is the concentration of NO. Concentration of NO is 2x. So we say, always use parentheses, 2x squared. Very important. When you're practicing, please don't take shortcuts. And now a lot of you love take shortcuts, but I've seen a lot of mistakes as a result of doing that. And I'll show you why. And the concentration of N2 is this. So that will be 0.033 minus x parentheses times concentration of O2, equilibrium concentration of 2, which is this 0.00810 minus x, close parenthesis, and that is equals to 4.8 times 10 to the negative 31. Let me show you a common shortcut people do. Here it says concentration of NO squared. And the concentration of NO is 2x. So we need to square that. Commonly, let me put it here. Let me put it in red to show that a mistake is possible. So let's say we have a concentration of NO square. What some people does is plugging in here. This is 2x, and they just do this 2x squared. We're not using the parentheses. What do you think about this? Here you will get right away something like it's totally wrong. 2x squared. And we can, or if I see that, this is what I'm going to do. Zero credit for that. Zero credits for that. Wrong. So don't take shortcuts. Most of the times, your shortcuts will lead to a grave mistakes. So put on parentheses. This is totally different. Look, concentration of NO squared equals 2x, that's the concentration of NO squared. And how much is this? This is 2 squared, which is 4x squared. This is correct. This is wrong. Why did this happen? Because you were taking shortcut, because you are in a rush. So take your time, especially when you are practicing at home. Relax. Do it calmly. Take all the steps, analyze, do critical thinking. That's the purpose of practicing. And then do one more, and then you start doing faster and faster and faster. Probably when you go to the test, you will say, oh, I don't have enough time. Now you are confident, and I'm sure maybe you can do this on your head. And you don't have to spend a lot of time writing down, because you already know this, and you can do it on your head. Here, you can do this on your head, and you don't need to write this, just write right away 4x squared. But you can do that only because you already did it the long way at home. If you keep taking shortcuts from the beginning, you will get the same mistake, even during the test. All right. Having said that, you will notice right away that we'll get a really interesting equation here. Let me I'm not going to solve the whole equation. I'm going to leave it for your homework, and I expecting you, some of you, post your result of this on the Blackboard discussion portion. It's open there. So once you solve this part, I want to see you post your result, the way you solve it, post it there, and I'll give you credits for that. So everybody can see that. Post your result, everyone, please. I want to see everyone's effort on this part, how to solve this equation the long way. So let me break this down a little bit for you. You do cross multiplication here, and you will get 4x squared, which is this, equals 4.8 times 10 to the negative 31 times 0.033 minus x times 0.00810 minus x. I know what you're thinking. You already started to suspect that once you solve this, once you simplify this and you work it out, you will arrive to something really scary. This. You will arrive to a equation with this shape. Ax squared plus bx plus c equals 0. Really scary equation for you, and that we call quadratic equation. And you know the only way to find the values of x is by using your quadratic equation. And you know, after you use the quadratic equation, you will get two roots, x and x prime, two possible results. That's not either ideal situation, ideal case. Here you see, this is the x. When you plug the plus, you get one result. When you plug the minus, you get a different result. So you got two possible roots. I explained that in the previous video. What will you do? Which one of these x you will use to solve your equation here? You will use the one that makes more sense. I explained that in the previous video, so you can watch it again. So again, I'm going to leave it here for you to solve this equation. Post every one of you, boys and girls, please solve this by hand, not on your calculator, because I know the graph calculators can do it by hand, everyone. And now, if you feel you are very expert solving these equations in the in your scientific calculator, graphical calculator, well, I invite you to show us your skills. Why not? We need to learn how to use this technology, this tool, the scientific calculator. It's important also to learn how to do it. If you feel you are good solving this equation also on your scientific calculator, show us how you do it. Record a little video, you can post it there. Or show us on the Blackboard discussion. I'll give you credits for that too. But also show me how to do it by paper, by hand, on a paper. Post that answer there. It's going to be really interesting. But we have tricks. Yeah. Here is the solution, the actual solution. Yeah. You see? Um, we have a trick. We have a shortcut. And I'll show you that shortcut, how to solve this problem without going through this pain on the neck of equation. There are shortcuts, but it's important to know how to do it. Okay, sometimes you cannot take the shortcut, so you must do it. All right, this is the analysis to do a shortcut. Look, and most of the times I encourage you to use the shortcut. During the test, again, I'm going to place only one equation, one problem where you need to use the quadratic equation. You cannot take the shortcut. But if you have to take the shortcut, if you can take the shortcut to solve this quadratic equation, or better, to not solve the quadratic equation. I have seen the students in the final exams doing the quadratic equation when they were able to take a shortcut. And I'm really impressed because they are good. When they do the solving the quadratic equation, they are really fast and they have the time to do it, even when they didn't need to do it, because there was the possibility to take shortcuts to avoid the solution of that quadratic equation. Here is the situation, and this is the analysis. Look, this number here. How small is this? We said this is really, really small number. Therefore, if this number is really, really small, that means the x, the change we are expecting here, is going to be really, really small. Very small. So if we are expecting x to be very small because the equilibrium constant is really, really small, then we can make approximation here. And we can say, you know what? Let me rewrite this one. Let me go back here. I'm going to look here instead of going back up there. So it's easy for me to stay on this slide. But these numbers are the same I have up there. Here. So let's say the equilibrium concentrations from there, we say the equilibrium concentration of N2, the equilibrium concentration of N2 is 0.033 minus X. And the equilibrium concentration of this is O2 equals 0.00810 minus X. Let's put that in parentheses. I just need these two. This is the analysis. Again, looking at the equilibrium constant, which is, okay, see, let me put it here, 4.8 times 10 to the -1. And you're looking for the order of magnitude, this number. The order of magnitude is 10 to the negative 31. Really, really small number. So again, if this equilibrium constant is very small number, then we are expecting x to be really small. About half of that sometimes. About half of that. How much is half of this? It's about negative, let's say around negative 15. But negative 15 is still a really small number. 0.0000000. It's a very small number. So we're expecting x to be a very small number. And what will happen with this subtraction here? 0.033 minus a really small number will be how much? About 0.033. Don't you think? 0.033 minus 0.0000000, small number, is about 0.033. It's not going to make change. It's not going to make any significant change on these numbers using these number of significant figures. So you say use is the symbol. It's not equal. It's not going to be equal. Of course, you have this number and you take even a very small amount, it's not going to be equal, but it's going to be about the same, with little, very little change to that number. So we use this symbol. And we write down the explanation why we are doing this approach, why we are doing this approximation. This is an approximation. This is not the actual result. This is an approximation, and I think we're going to be good because the error introduced by this approximation is going to be very small, and we can deal with that error during the experiment. There's a rule, even a rule that tells you when you can make that approximation. And I'll show you that rule later on. Right now, since we have this very small number, we are safe. The error introduced by this making this approximation is going to be very small. Similar here. We have 0.00. This number is even smaller than this. It has one more zero. Minus a very, very, very small number, still that symbol is like an S lying down. Yeah, like that. 0.00810. It's going to be about, we explained that, Because the value of kc is too small, we expecting x to be x small. You write that down in your test. Explaining why we are doing the approximation, and you can say the error introduced, so you recognize that it's going to be error. The error introduced into this is going to be very small. And we can even calculate the error introduced there. And later we are going to compare with the actual value to see if we really have a small number and if we were correct doing this approximation. Now, by doing this analysis, we simplify the whole process a lot. Because now on the expression, equilibrium expression, we'll have 4x squared divided by 0.033 times 0.00810 equals the equilibrium constant, which is 4.8 times 10 to the -31. Look, this equation is a lot easier to solve than this one here. This will lead us to a quadratic equation situation, whereas here we went around and we can solve this using simple math, no quadratic equation. Because on this one is just simply reorganizing terms, and you will say that for x squared equals first term, well, actually, let me put the number first. Yeah. 4.8 times 10 to the negative 31 times 0.033 times 0.008110. You multiply, do this multiplication very simple in the calculator, and then, and even further, you say x squared equals that number divided by 4. Whatever you get there, that multiplication divided by 4. And then x is going to be what? How do you get rid of this square? Take square root on both sides. X is going to be, you take square root on both sides, you will have, let me put it here. You say square root of this equals the square root of that number. Let's call this number here. Let's call, when you do the calculation, I'm not going to do it now. You can do it. You are the one interested on getting the skill. A equals A divided by 4, and you get, and then you say x is going to be, because a square root of x squared equals x, and then you get a number here, because you have a number and a number, do this division, then take square root and get, that's your result. And that result happens to be 4.01, so 8.01 times 10 to the negative 80. That will be x. You see, we did this in less than 1 minute. If we were to solve, and you're going to do this, and tell us how long you took to solve this equation. Now, we were expecting a very small number. Look, doing the approximation, 8.01 times 10 to the negative 18 is very small number, and that will not make change here. And you compare that to the one that you get from the actual solution of the quadratic equation, you will see no big difference. And then, and this is x. Now we can plug that into here. We plug that into here. What is it? Into here to get the actual concentration of N2, and into here to get the actual concentration of O2. And into here to get the actual concentration of NO. 2 times X is the actual concentration of NO. So that's what we have here. 0.033 minus x, which is 8.01 times 10 to the negative 18, doing the approximation, and you get this result. Same thing here. Very little change, and you will find the concentration of NO 2 times X, which is 1.60 times 10 to the negative 17. Look, the concentration of NO at equilibrium. This is the actual concentration of NO for this particular problem under these conditions. This is what you have at the equilibrium at 25 degrees Celsius and 1 atmosphere pressure for that reaction when you put these initial amounts. Look, very, 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 very little. That's what I said. Remember I said at the beginning, this reaction, the value of the equilibrium constant for this reaction is telling us that this reaction is basically not making products at all, very small amount. And the main reaction here is the reaction, the reverse reaction, because at the equilibrium, mostly all reactives maintains unreacted. This is what you put the initial, and this is at the equilibrium. Basically, it's the same, unreacted. So that's how you solve problem. I show, by showing this solution of this problem, and by doing all this critical thinking, I'm giving you an important tool for you to solve practically any equilibrium problem. So you can follow this and practice and go over and listen to my analysis, the critical thinking we are doing here, and you can practically use this as an example to solve any equilibrium problem. Here on this one, I'm going to do only one of those. Let me see. Let's see. Here, to write the appropriate mass action expression for this, we need to check if we have homogeneous reaction or heterogeneous. Here, homogeneous, we have to use all of them in the equilibrium expression. Here, we have heterogeneous because this is solid, and this is gas. This is gas, I'm telling you that. So you use only gas, and this is the equilibrium. Here, we have solid. This is aqueous. This is aqueous. So we use only aqueous. Here, only gas. Remember, in the expression, we include only species that are in a gas phase or aqueous. We do not include solids or pure liquid. When it says here liquid, do not include that into the equilibrium expression. So for this one, let me do this one, the equilibrium, and you do the rest. For this one, the equilibrium constant in terms of concentrations equals concentration of N, double check is balanced. This is 1 CO3, 1 nickel, is balanced. It's going to be nickel 2 plus times concentration of CO3 2 minus over concentration of NO3. But since this is solid, we don't write it here. So basically, we don't need a line. And I will, to make it nicer, probably I will rewrite it and say equilibrium constant equals, in the same line. In the same line, you see here? In the same line, and it looks nice. Yeah. No one here, up there. So when you're writing, this is a neat way to write equations, solving problems, you write equilibrium equals, and the line should be right here in front of the equal sign. I have students doing this, equals, and they write the line over there. Or some write the line over here. It doesn't look good. Like that comes especially when we write something like, for example, let me do this. Some people say, okay, A times B, and then equal, sorry, over C. You see, that is not good. And so that the best way is you say, okay, if you know you are going to write a fraction, so write the line first. And now you say A times B over C. Probably when you went to your elementary school or even high school, nobody there to teach you properly how to write equations. And probably that person, or your teachers, thought that it's not important. It is important. When you write neat, you put in that neat information into your brain, and we can lead to less confusion, less mistakes. And get used to it. Just get used to it. The same way you get used to do wrong. I'm not saying this is bad. I say it's not well organized. If you get used to write things in a not well organized manner, why just don't start getting used to writing things in an organized manner. The Chatelier's principle, this is really interesting, and I explained this already. All possibilities here, making changes on the concentration, making changes on temperature, on pressure. I love this. This is really good stuff. I leave this for you. I know you can do it. I know you can do it. And you can write your answers of this on discussion to discuss with your partners. Especially if you have doubt in some of those, write it down. I want to see where you're struggling so we can help you. We all as a community, Chem 12 community. Now we belong to the same community and we take care of each other. All right, I'll be there monitoring in case something I don't feel is correct or something that can be done better. All right, but please, everyone, show your work on your Blackboard discussion portion. Now you have enough tools to do this too. I give you enough tools. Oh, we already solved this. Oh, okay, this is already solved. All right, the same problem. This is the same problem. It's already solved. What about this? I already gave you tools. You can solve this. And this one, I leave it to you. So you decide if you are going to take a shortcut or not to avoid the solution using the quadratic equation. I solved one of those problems, so I think you are able to solve this one too. Right, so leave it to you too. You get a trouble, you get stuck somewhere, you try it, you cannot do it, please let us know on the discussion. So that will give me more chance to explain again. But I would like to see your inputs first in the Black board discussion. I don't want to receive answers of this through the email, like receiving homeworks. Put it on the Blackboard instead. Blackboard discussion. That will be more beneficial to all of us. So any of you can actually pop up and say, hey, I have the solution for that. And let me show you what I did to solve that. And maybe somebody else says, oh, interesting the way you are solving this. I also find different way to solve it. So we'll see. And then you can choose what way you want to do it. Or sometimes, or somebody can pop up and say, hey guys, I think you are making a mistake here. And this is the way to correct it. I will be there monitoring all this discussion. And I would like to see everybody involved there. Even if you agree and you already understand and you have no problem, just write it down. You say, I agree. Sign it. I know, so I know you are being part of the discussion. All right. I'll leave you there. This is the end of chapter 14. I'll see you in the next chapter. I'm making up with this recording. I'm very happy now with this new format. I'm using Zoom and Notes. I'm very satisfied. I have initially huge problems. I lost a lot of time using Blackboard Collaborate. Last semester it was working fine. Now this time, I don't know if that was my computer. I had to change, reformat everything. I even try using different browser, but obviously it didn't work. My recordings came out really bad for sound and for video. Anyway, thank you. I'll see you next time. Stay safe. Keep you safe, family. The virus is still there. COVID-19 is still there, is out there. Don't fool yourself and think that this is over. And you've been healthy so far because you were quarantined and you didn't get it. You didn't get sick because you were protecting yourself and you were protecting your family. And that's why you are healthy now. Thank God. And you're healthy now because there's no virus. It's because you were protecting, you were quarantining. So virus is still there, it's outside. When you go outside, take all the measures, all the precautions. Use the correct PPE to protect yourself and encourage your family members to do the same. So stay safe and stay healthy. See you next chapter.